All right. So last time we talked about the natural numbers, and I gave you a very informal description of how you could construct them, but I did not and will not give you a construction of that today, because as you know, we're following this theme that you can't really prove everything. You must start assuming something. So the thing that I did mention about the natural numbers is how they are constructed as a set, but I didn't really talk about the structure that this set has. And this set has two important structures on it. It has an order structure and it has an algebraic structure, right? There's operations on the naturals that you can use and that all of whose properties you're able to assume from now on. We won't prove any of these properties because I haven't defined any of these operations, right? I haven't told you how to add two natural numbers or what it means to add two naturals. So there's no way for me to prove to you that addition is, say, commutative, right? Because you can ask, well, how do you know? How do you add two numbers? Just in case you're curious, you could define all of this recursively, and you can prove all of this inductively, right? Recall that recursion is a way to define things, and induction is a way to prove things, even though both are the same thing, right? They follow the same basic principle, the same property on the natural numbers. Okay, so here's the algebraic approach to introducing the natural numbers. It's the same set, of course, but here I am not worried about the set, about the elements, about the naturals themselves, but rather how they interact with each other in this algebraic setting. So something that I just want to quickly define to you is what a partial order is. This was also defined in the tutorials, but let me just repeat this. So a relation on X, which we denote by a very familiar symbol, the less than or equal to, is a partial order if it is reflexive. So every element is less than or equal to itself, because of course it's equal to itself. It is transitive, which I'm sure you know if A is less than B and B is less than C. Well, of course, we expect A to be less than C. But this relation, unlike equivalence relations, is not symmetric. Symmetric, again, means that you can always switch the order of the relation. But this wouldn't make sense in an order relation, right? Because in an order relation, we want this to tell us what is bigger and what is smaller. So if you could just swap them out, well, you would lose all that information. So this is not just not symmetric, it is the opposite. You can never swap out the order of two elements unless they are equal to begin with. Let me try to highlight what I'm talking about. Unless they are equal to begin with, you cannot swap the order, right? So the only way that you have both let's say relation types, so A less than B and B less than A, the only way that could happen is if A was B to begin with, right? In any other case, you can only have one of those two things. Right, so that is what a partial order is. We will see many examples of orders and partial orders. We already saw one, right? Containment on a big family of sets, for example, the power set of some universal set X. This is a partial order, and we verified these things. Maybe not with full detail, but they are written down somewhere in the lecture notes. Okay, that's a good question. Someone asked in the chat, is the equality symbol always defined as an equivalence relation? So yeah, the equality symbol always satisfies all three properties of being an equivalence relation. Now, it is not really an equivalence relation for the same reason that the example of lecture 3 is not really an equivalence relation. Maybe I can go back just a little bit and show you what I mean. Last time I defined this symbol that you can see at the top of the screen, just notation, and it is technically defined in terms of the equality symbol, right? And I said that this is not really an equivalence relation, and the only thing that fails is that an equivalence relation is, well, a relation to begin with, but relations have to be defined on sets. But in this case, what would be the set that this relation is defined on? It seems like that would have to be like the set of all sets. And we didn't see axiomatic set theory in this course, but if we had done that, I could convince you that there is no such thing. So the set of all sets is actually too big to be a set, and thus this is not really a relation. It is something more general than that. But to answer your question, yes, the equality always behaves like an equivalence relation. It is always symmetric, reflexive, and transitive. Yes. One of these technical nuances that aren't really that important unless you're trying to do things from the ground up, closer to the ground up, which is not what we're doing. But yes, that's a good question. So let me give you one very abstract definition of algebra, which is called a monoid. Now, this definition is part of the notes and of the lectures. We won't study monoids in an abstract sense. I won't tell you, okay, let's see these properties on general monoids. And for that reason, this is not something that you're supposed to know by memory. You're not supposed to memorize this. In the exam, I will not ask you prove that all monoids satisfy this and that and its implication. That will not be the case. But again, this course is not just an introduction to proofs, it is an invitation to more abstract math. So by giving you this definition and some examples, I hope that you see connections between different things that you may not have realized were actually intimately connected. And one of these connections is, well, algebra, right? So let's say that X is a set, and this is probably not a very good notation, so I'm going to change it as I go. Instead of this symbol, let me maybe add an asterisk or something. So an operation or a binary operation is a function whose domain is x cross x for some set. So you're taking pairs of elements and you're outputting a third element in the set. So you're probably familiar with this notation where instead of writing the function the way we usually write it, you put the input in parentheses and then the output to the right side. You can just put the symbol of the function in between, right? Because it's like you're combining two elements to produce a third one. A classic example of a binary operation is, of course, addition and multiplication and subtraction and set difference and exponentiation. And there's a million examples of this, right? You use binary operators all the time in pretty much every mathematical field. I am also going to fix some fixed element E in X, a distinguished element, and I will tell you why it is distinguished, what makes this element special. Then this structure, the set X with this binary operation that I just defined, and this element E is called a monoid if the following three things hold, which I'm sure you've seen mentioned before. It is going to be a little bit tedious to change. The reason I don't want to use the little round symbol is that it might be confused with the function composition that I defined last time, and that will be one example of a monoid, but this is supposed to be an abstract definition. Next. Okay, so what is this very abstract definition? I know many of you, if not all of you, are seeing this for the first time, so don't worry if you don't understand. We will look at some examples, right? So a monoid means that, first of all, the operation is associative, right? The parentheses, where you put them doesn't matter. If you're operating on three elements, x, y, z, if you first do x, y, and then z, it doesn't matter. It will give you the same result as if you do x, y first and then z, right? Associativity is very important, and all the interesting operations that we will ever talk about in this course have to be associative. Because if they're not even that, well, they don't have enough structure to produce anything that we will find interesting in this case. And the second one is that E behaves like an identity element, like a neutral element. Whether you act with E on either side of an element, it won't change that element. It will always output the fixed element X, right? So E does nothing. It behaves like zero in addition, right? Adding zero on either side doesn't change the number. Now, a commutative monoid is the same thing, But you have the additional property that the order of the operation also doesn't matter, right? So x operated with y is the same as y operated with x. You have many examples of this. For example, if you've taken linear algebra, then matrix multiplication satisfies all of this, but it is not commutative, right? The order in which you multiply matrices does matter, even though it has an identity, which is the identity matrix, and it is associative, right? Actually, maybe I should have written that example down. I think I didn't. So let me give you two examples of commutative monoids that is very easy to verify based on properties we already saw in the lectures. Take the power set of some set, then the union forms a commutative monoid, right? The union is commutative, it's associative. What is the identity of the union? If you have a set and you want to take it with the union with something so that it doesn't change the set, well, the empty set is the obvious candidate, right? If you have a set A and you take A union the empty set, well, that's just A. You didn't add anything to A. So the empty set is the identity of the union, right? It doesn't affect the union at all. Similarly, the intersection forms a commutative monoid, but this time what set doesn't affect the intersection? Well, if you intersect with the big set, with the total set, like the universe set, right? Intersecting with that changes nothing because all subsets are already, all sets in consideration are already subsets of X, right? So verify in your own time if you want that this indeed satisfies the definition, but we already wrote down this explicitly in the past. Okay, let me see, I got a question. Can the set itself be candidate for both cases? Let me think about this. Okay, so the problem with taking the union with capital X is that if I do that, then I may not, I mean, I always get a subset of X, but I always get the total, right? So if I understand the question correctly is, why do I have the empty set here? Couldn't I just write X? Because if everything is a subset of X, then taking the union with X will just give me the same element, right? But I don't get back the same element. I always get X. So that would be a different type of thing. That would be like multiplying times 0, right? Adding 0 doesn't change anything about the number, but multiplying times 0 always gives me 0. So that's a different property, even though they're related because they give you the same thing, as in they give you a constant predictable thing. This would be different. But that's a good question, and that actually motivates the next definition, where I combine a monoid, two different monoids, two different operations. I combine them into one. Okay, yes, yeah, you're welcome. So another example is if you take the set of all functions from x to x, and we denote this as x to the power x. Why is that do we denote it like an exponentiation? That will be made clear in chapter 4. So right now, just take this as notation. We won't be dealing with this in detail right now anyway. So I already defined to you the composition of functions, and you also know what the identity function is. Well, this forms a monoid, right? It is associative, as I haven't mentioned, but you're welcome to verify yourself. The identity behaves as we would expect, right? That's why it's called the identity function, because it is the identity of this operation. If you compose with the identity on either side, you change nothing about the function. Now, there is one mistake that is currently written in my notes. There's one property that this doesn't satisfy. Can you tell me what that is? Maybe I should add a number here for easy referencing. 3. So a monoid satisfies two things. A commutative monoid satisfies three things. And indeed, composition of function is not commutative, right? Why is it not commutative? Well, composing functions is like you're doing an action and then you're doing another action. So it's not too hard to see why this is associative, and you can verify this just by the definition, right? But why would it be commutative? It's like you're doing an action and it follows by a different action. For example, if you multiply times 2, that's an action. And then you can add 4, that's another action. There's no reason to expect that multiplying times 2 and then adding 4 would produce the same result always as first adding 4 and then multiplying times 2. In fact, it doesn't, and I just gave you a counterexample. So this is almost never a commutative monoid, unless perhaps in very specific cases where X is like singleton or an empty set or something like that. So this is not a commutative monoid, and I made this mistake. You should now have enough information to answer the weekly quiz. Should be available on Quirkus with the last example. Okay. So let me just tell you how to combine two operations into a single set, because monoids are just one operation. So how do you combine addition and multiplication? All the structures that we will talk about in this course have two operations, addition and multiplication. So of course we need a way to combine these, right? So look at the next definition. This time we have two binary operations, and I'm already using the symbols plus and times, like little dot. They could be defined differently. I'm not saying that this is the addition that you are familiar with from natural numbers. I'm just using the same symbol because, well, that's in most cases what we're going to use it for anyway, right? And this time we need two distinguished elements, 0 and 1, because one of them will be the identity for the first operation, addition, and the second one will be the identity for the second operation, which is multiplication. I am calling these elements 0 and 1, but please keep in mind that they may not necessarily be called this way, right? And I will give you examples of this in a second. So a commutative semiring, and I think I only care about commutativity this time. I'm not going to split the definition into, well, if in addition it's commutative. I think we will only care about commutative semiring anyway. So a commutative semiring is a set X with two operations, plus and times, and two identity elements, 0 and 1. They are the identities respectively, right? So a very succinct way of writing this is X with plus and 0 forms a commutative monoid, and X with times and 1 forms a possibly different commutative monoid, right? So I haven't told you that 0 and 1 should be different. In that case, these could be the same monoid, and like both operations could be the same. Of course, in a practical way, I will never do that, because then why would I bother introducing two operations if they're just going to be equal? But yeah, obviously in the natural numbers, it is the case that 0 and 1 are different elements, right? I'm just saying this in case you want to explore the possibility of a singleton being in a commutative semiring, which I think it would be, right? The only element being 0 equal 1, and the operations can only be defined one way, right? So there's only one commutative semiring structure on a singleton set. Okay, let me see where I left off. So that's a commutative monoid, and I need a way to combine the operations, because otherwise it would be, what's the point of introducing two operations on the same set? And the way that you combine these, the way that two operations interact is called distributivity, right? And it's a rule that you're, I'm sure, familiar with, right? X times y plus z is the same as you multiply out, right? Or you factor x, depending on what direction of the equality you're looking at. You're factoring x to the left side, or you're multiplying out to the right side. And this is called distributivity. And all the semirings that we care about will have this property. So let's see what examples I wrote in anticipation. So okay, I think I only have one example. So the only example that I have right now, but every structure that we will study in the future will also have this property, so it will be more relevant as we move along. A power set with the union, the intersection, the empty set, and X is a commutative semiring. The only thing left to verify, given that we already know that union and intersection are monoids, the only thing left to verify It's that union distributes over, sorry, I think it's usually said the other way around. It's that the intersection distributes over the union, right? They have this distributive property. And if you're curious, in one of the additional problems of the first problem set, you have to prove a very generalized version of distributivity. Distributivity here is just a binary thing, right? It's just, okay, you have two elements, x and y, and you're multiplying two at a time. But we already know that the union and the intersection can be defined in a much more general setting. It's not just the case that you can take the union of two sets. You can take the union over infinitely many sets. So the question on whether this is still distributive holds, and this is answered in the problem set. The answer is yes, it is as distributive as you want this to be, because this is not just a commutative semiring, it's a lot stronger of a property. Last lecture, I already mentioned that this is a lattice, and I may have even mentioned that this is a complete lattice. Moreover, if you're curious about me you're spitting out random definitions that you can Google if you want, this is a Boolean algebra. So it's the strongest algebraic property that you can have in these types of things. So this leads me finally to the point that I wanted to make in this first part of the lecture, which is that the natural numbers form a commutative semiring. And I will not prove this to you. This is why this is a theorem slash definition, because I can't prove this. I didn't tell you how to add 3 and 4 together by definition, but you already know how to do this, and your working knowledge of the natural will be enough for this course. So this is our starting point for this course, and this is all you have to do. Now, one exercise that I recommend you do so that you know exactly, this will answer all the questions that you may have on, wait, what can we use when we're writing proofs on the natural numbers? Can we assume that the natural numbers have this or that property? Well, this is exactly the properties that you can assume, that they form a commutative semiring. So my advice to you is, why don't you write out what this means without using any of the words that I just defined, right? So forget about monoids, forget about semirings, forget about any of these words of distributivity. This should be, I don't know, something like 8 or 9 axioms on the natural numbers, and they will look like the natural numbers have two operations, plus and times, two distinguished elements, 0 and 1, and they satisfy that x, any natural number plus 0 is just x. Any natural number times 1 is just 1, and so on, right? And of course, you can prove things about the natural numbers that we haven't proved until now. For example, that multiplication times 0 is always 0. But that will all follow from the things I already wrote down. This is like the least you have to assume on the natural numbers so that we can work with them. And this finishes the introduction on everything I have to say about natural numbers. Let me just tell you one more thing that I forgot to write down here, and I did not do that. Okay. In the meantime, feel free to ask questions or take a look at the quiz that's already available, the weekly quiz on Percus. And just give me 1 minute. There's a partial order on the natural numbers, and that's also important for me to mention. So there is a partial order. And it's not just a partial order. There's a partial order on the natural numbers. It's not just algebra. We also have order, right? The natural numbers are ordered on a line. And the rational numbers, the integers, the real numbers are also ordered on sort of the same line as we extend it. Not all structures that we will construct in this course are ordered in the same way. Like, I think we won't mention the complex numbers, but those are not ordered, right? In a compatible way, at least. There is a partial order such that two natural numbers, a is less than or equal to b, if and only if there is a c natural number, of course, such that a plus c is b, right? This is one way to do this. Okay, so some people cannot see the weekly quiz on Quirkus. Okay, I will rectify that in the pause. Let me just finish this, and don't worry, you'll have enough time during the lecture to do that. Okay, so you have this partial order. If I change this to multiplication, by the way, this part here to multiplication instead of addition, I get a different partial order. And that one is actually not even a partial order. I mean, it will be a partial order on n, but not when I define it on the integers. And you'll see why next week, hopefully, or maybe the week after that. Okay, this order is not just partial, has an additional property. It is linear, or also called total, also called trichotomy law. Trichotomic, I guess, or satisfies trichotomy law. And what that means is that for all AB natural numbers, either one of them is bigger than the other, right? Okay, so some clarification in the chat. The weekly quiz is available under the grade section. It should be also under assignments, if I'm not mistaken, but I will address this in a second. Okay, so this is pretty much everything that there is to know about the natural numbers. As sets, they satisfy induction and will ordering, which we will cover in more detail as we have more relevant examples, right? I mentioned, but I didn't explicitly write down that there's something called strong induction. There's something called, structural induction. There's no point in me in just listing these out without giving random examples. We will talk about this in possibly next week when we have more interesting examples to work with. Okay. So that is as sets. As algebraic structures, they form a commutative semiring, and this is pretty much everything there is to know, everything there is to say about the naturals. And as an ordered structure, they form, well, a linear order, right? So linear means that you can compare any two sets with a relation. That is not necessarily the case for other types of relations, right? Okay, so this finishes this brief introduction to the natural numbers, which is more of a way of me saying this is what you're allowed to assume for the problem sets and so on. I know we haven't covered that many proofs in this course, but we will do this in the second half of this lecture, because of course that's the main part, but we did need some foundations, some definitions to work with, and we will work on a lot of these things. Let me maybe pause here.